Welcome to class. In this video, we're going to learn about reduction of order. Reduction of order, as the name implies, is a way to reduce the order, go figure, of differential equations. Here I have a second-order differential equation that we already have the general solution of. It's c1 e to the 2x plus c2x e to the 2x. And you can solve this very quickly using the characteristic polynomial since it's homogeneous. However, I want to show a different way of finding the solution. I want to use reduction of order here as some justification or proof of concept. The idea is that I'm going to rewrite this one second order as two first order equations and solve the resulting system of first orders, because sometimes working with a bunch of first orders is better than working with one high order equation. The way I do that is I call each of the derivatives a new variable up to the penultimate derivative. In this case, there are only two derivatives, so I'm going to give a name to the first derivative. And let's call it, let's let y prime equal v for now. We'll call it v. Then I can rewrite the differential equation as v prime, since y double prime is y prime prime, minus 4v plus 4y equals 0. Do you notice here I have two equations with two unknowns, those unknowns being y and v. So I can rewrite this as the system of equations that y prime equals v and v prime equals 4v minus 4y. Or in matrix form, if I call u the vector y comma v, then I can write this as the matrix 0, 1, negative 4, 4 times u prime. This is still a homogeneous equation, and it's a system of first orders this time, which means finding the general solution is as simple as finding eigenvalues and eigenvectors. It turns out that this matrix only has one eigenvalue, and that's 2. And its corresponding eigenvector, v1, is 2, 1, or at least has that form. And I can generalize an eigenvector that's linearly independent based on this one of the form negative 1, 0. Remember then, the general solution is that u equals a constant times e to the lambda x v1 plus c2 e to the lambda x x v2. But here, the top row of my matrix equation corresponds to y, and the bottom row corresponds to y prime. Really, it's just the top row that matters. This tells me y of x is equal to c1 times 2, which I'll just absorb in, e to the 2x, plus c2 times negative 1, I'll just absorb the negative 1 into the constant, x, e to the 2x. And you can see that this gets us the same solution. Now, in the second order case, it's maybe a little overkill to use reduction of order. However, I can use it in higher dimensional cases, and here I think is where it really shines. Sometimes factoring or finding roots of very high degree polynomials is difficult to do by hand, but I can still reduce the order of this equation. I can let y0 equal y, y1 equal y prime, y2 equal y double prime, so on and so forth until I let yn minus 1 equal y, the n minus 1th derivative of y. And then I can rewrite this system of equations as first order matrix equation, or a system of first order differential equations rather than a single nth order.